This podcast is brought to you by HEC Paris.
Thanks. So I'd like to thank the speaker for putting together such a nice conference. And I'm going to discuss Yassin's paper. And this is actually a very timely paper after the 2007-2008 crisis, where we saw a massive example of contagion from the real estate, US real estate market to Wall Street, and finally to all the stock markets in the world. And there's a saying that goes, when Wall Street sneezes, Paris catches a cold. Some people say Paris catches pneumonia sometimes. This is true of pretty much every financial places along with Paris. And I would say that this paper is a kind of mathematical elaboration on this simple saying. So, of course, when we model financial crisis, capturing contagion is crucial. And there's both a spatial dimension and a time dimension, because crisis on one market is going to cause other crises on the same or on other markets. And this is not simultaneous. There is a time lag that separates the first crisis, the causing crisis, and the subsequent crisis. So the paper does this using those Hawk processes, which have been applied in other fields of applied statistics. And the basic equation, this is the same equation as was in Yassin's talk. So you can see that it's basically a stochastic volatility model where you add those jumps. And as Yassin was saying, those jumps have an intensity that is increased by the occurrence of past jumps in the same or in other markets. And there's also some mean reversion, which, as Yassin was saying, is what you need to get a stationary model. Now, let me make a first remark about this setting. And I do sympathize with the reduced form approach. But there's one flavor of the model that I would like to know whether you could extend this in order to make it maybe a little bit more realistic, is the fact that when you see how intensity is affected by the jumps, intensity is affected by the occurrence of jumps. Okay, it's by discounting process here, dn. And it doesn't take into account the fact that the jump is high or not. So basically this z, which is the side of the jump, is basically whether the crisis is serious or not, whether it's it's actually a crisis or whether it's good news on a market that makes prices jump up. And you see that this z random variable is completely ignored into the process lambda, into how it affects the intensity of future jumps. So my first question to Yassin, actually, I'm going to ask is can this be extended to a situation where the intensity would reflect the size of the jumps? My next slide, sorry about those nasty-looking formulas. It's just a remark to say that if you write down the evolution equation as it is in the paper, you have the equation that's driving the model, which is not a partial differential equation. It's an integral differential equation here because of those jumps. It pretty much looks like a standard equation, PDE, that would drive a stochastic volatility model, apart from the fact that you have those terms that are due to the jump processes. And you can formally solve this equation, and this is what the way the moments are derived. And this brings me to a question I'd like to ask you, Yassin, about the possibility of an alternative method. So we know that there are alternative volatility estimation methods, such as the one by Hansen and Shankman, who actually work directly on this operator that I showed just before, this infinitesimal generator of the diffusion. And the way they work is that it's a spectral method. They look for eigenvector of this operator. And because they find eigenvectors, integrating the equation is very simple along the eigenvectors. And it turns out that in the case without jumps, those eigenvectors are very simply related by a simple differential equation to the diffusion parameters. So I'd like to know whether this extends in this case, and whether there's a simple relation between the process parameters and the eigenvectors of the equation that you can compute numerically. Okay, my final remarks will be economic order. So my first remark is that here we saw a stationary model, but I'd like to know whether it would be possible to test whether there was some evolution. We know that there was a process of financial integration, that markets get more and more interdependent, so more and more financial contagion. I'd like to know if we could use this approach to test whether there is pattern in contagion process. So can we find maybe structural breaks in those correlation patterns? Second remark is to relate this to what's been done, especially by Barrault, to look for an explanation to the so-called equity premium puzzle, which is basically that mean return of stocks are abnormally high. And Barrault argues that there is much more risk than you would think due to crisis, due to jump processes. And I'd like to know if this paper could be used to solve other puzzles, empirical puzzles, such as the home bias puzzle. People detain more stocks of their own country than other countries, contrary to what theory would predict. And here maybe the argument would be there is more correlation than you think due to those processes. And my last point was partially answered by Yassine about causality and directionality, so I'm not going to elaborate on this. And I'm done.
Thank you very much.
Maybe I'll take your questions in reverse order, since they're probably fresher in people's mind that way. I think certainly on the home bias puzzle, you do have a point there. What the model generates is the fact that in times of crisis, all correlations jump to 1 or near 1 among all asset classes. So if you're aware of this, then certainly diversification, or at least international diversification, looks a lot less appealing to you as an investor. And in a sense, that's why the optimal solution in the portfolio sense tells you to run to the exit indiscriminately as soon as you see an increase in lambda for whatever cause. If you have this sort of cross-sectional contagion, you're going to run out, and do a flight to quality and go into U.S. Treasuries or bonds, German bonds, or whatever it is you think are safe in that time. So that's definitely right. You ask about testing whether there is more and more integration over time. So we have GMM estimates of these things. We have standard errors. We could certainly imagine doing Choute-like tests where you split your sample in two and you look at whether the parameters, like you mentioned, for example, the directional ones, delta 1, 2, delta 2, 1, you could check whether delta 1, 2 in this subsample goes up or from the other subsample. I mean, you could do all sorts of sort of one-sided or two-sided tests on this. So that we haven't done it, but that's only technologically doable with the existing technology. Then you asked about different estimation methods and doing sort of back to the future type of estimation. You're right, as you pointed out, that we have the full generator. It's a Markov process. We have the full generator. So we can certainly do that and take test functions and take the generator, take the time adjoint of the generator and combine the test functions as is required. I think to this I'll give you my response is sort of why we haven't done this, and we've used sort of classical moments, sort of mean variances, autocovariance. I'll borrow that. I'll borrow that from Nick Paulson, who told you that, he's done enough MCMC to know sort of when it works and when it doesn't work. And what I've learned with GMM, especially with large models that have lots of parameters. So for example, in the bivariate model, we have 15 parameters. So what I've learned with, in just practical experience doing GMM is that you are much better off if you have moments that almost separately identify separate parameters, even though, of course, mathematically everything is identified together. But you are certainly better off if you can say, look, these 4 moments identify these 4 parameters, and this moment identify this parameter, because you're much less likely to get stuck at a local extremum of the quadratic GMM criterion function than you would be if all 15 parameters are identified by 15 plus moment equations in a very large system without a clear mapping from if I really fit that moment, if I force this moment equation to be nice, then I know I have this parameter right. So at least that's my experience with this. So that's why we have moments such as the autocovariance moments that really identify separately the self-excitation moments. Then we have the skewness and kurtosis moments that identify separately the unconditional jump distribution. Then given this, the variance identifies the volatility moment and so on. So it makes it a lot more tractable in our experience. The first question you asked was about deficiency of the model, and I think I fully agree with this. It's actually a question we've been getting over and over again regarding why our intensities go up as a function of the number of jumps and not the size of the jumps. And so, in other words, as you noted, our lambdas go up by some parameter times dn and not by some parameter times zdn. Which would probably be more realistic in the sense that a particularly large jump, you would like a particularly large jump to increase intensities. You would also probably like negative jumps to increase intensities more than positive jumps. So you would probably like to also build some asymmetry to just keep on going with sort of the same line. We haven't done this because if you do this, then you lose the separability between the distribution of the jump between sort of the jump distribution and the self-excitation parameters in the cross-sectional moments. So the cross-sectional moments no longer identify that separately. So it's sort of tied back to the answer I was giving you earlier that it does make GMM in practice more complicated. Fundamentally, it doesn't change things in the sense that we can still calculate these things. I mean, things are more complicated because now the jump distribution enters into the intensity. So the intensity is no longer just an autonomous. Right now, the couple between n and lambda isn't just an autonomous process. It just evolves. It just evolves on its own. If you throw in a z in the middle, then the moments become messier. So that's the reason why we haven't done it, even though I fully agree that it would certainly be more realistic to do so.
Thank you, Yassine. We have a couple of questions, actually, in the back there. Go ahead.
So that was going to be my last application to option pricing. We haven't done it. In the case, so we haven't done any empirical work with this, but theoretically, if you take an affine model within this class, just like the Heston volatility model with linear mean reversion intensities and constant parameters, then your model is entirely affine. And you get option prices that are also exponential affine, just like in the normal affine. So you can actually calculate option pricing. You can actually calculate option pricing quite straightforwardly. And in fact, this is how originally Gisicki and his co-authors used self-exciting jumps. So in that case, their model was a pure jump. Since they worry about valuing credit derivatives, they worry only about default. So they worry about a jump that takes you from they worry about a portfolio of assets where you take one jump, where you take one asset, and one asset sometimes experiences a decrease in value to 0, perhaps to some recovery rate. But it's a pure jump model. And with an affine intensity, you will get just basically the same affine trick. So you can value derivative using ODEs and sort of the usual things you can do with affine things. So we haven't done it, but it could be done. Now, of course, with options, usually most options payoff we have are on a single asset. We don't typically tend to get sort of, I mean, there are some quantos where you could get sort of a currency and the payoff of a particular asset in a different currency. So you might get some interesting cross-excitation. But usually you would mostly see self-excitation, just the time series dimension in it. And so you could see it, but sort of over a short horizon, you would only see the time series dimension.
Please visit us at www.agc.edu.